So let's talk about the idea of infinite limits here for the next several videos. And like usual, let's first talk about the learning objectives. What is it that we want to get out of this next several set of videos here? First, I want to determine infinite limits from the left and from the right. So I need to be looking at limits from the right and from the left and talk about the idea of what an infinite limit actually is. Now I want to find and sketch the vertical asymptotes of a graph of a function, and these are actually based on these infinite limits. Let's start off with the definition. Now suppose f of x is defined for all x near c. If f of x grows arbitrarily large as x gets sufficiently close to c, that means I'm getting infinitely close to c, then what we write is the limit as x approaches c of f of x is equal to infinity. This is saying the thing blows up. And actually the term it blows up on you is actually a common term in calculus, and that actually makes reference to the fact that you're taking a limit and it goes to infinity. So suppose I have a function and it looks like this. Here's my x-axis, here's the y-axis, and here's some value c. So as I approach c, arbitrarily close, that means infinitely close to c, along the x-axis, if this thing is growing like that, and if I get arbitrarily close to c from the right, like that, see from both directions I'm going up to infinity. So the limit is infinity. And when we say that the limit is infinity, that's really also saying, and you should show me, that it does not exist. Because remember, for a limit to exist, it must go to a real number. And infinity is not a real number. Now, we can also address this from the point of view of one-sided limits. So if I approach some value of c from the left, and as I approach from the left, if my function, I'll draw the function in blue, goes like this, see now it's shooting down to negative infinity, and then as I approach from the right, let's say that it goes like this, now I have a situation where the limit as x approaches c from the left of f of x equals negative infinity, which means it also does not exist. And, sorry I'm running out of room, I need to come over here, the limit as x approaches c from the right of f of x this equals positive infinity, which also means or implies that it does not exist. So if we go to infinity as we approach c, then we say that the limit is infinity, doesn't exist. And we can have right and left hand limits go in opposite directions, which by itself tells you that the limit doesn't exist. But from the right we could go positive infinity, and from the left we could go to negative infinity. And in addition, we can take a look at the idea of a similar definition if f of x approaches negative infinity. So if I say the limit as x approaches c of f of x equals negative infinity, then what I just described is a situation similar to this, where as I approach c from the left, I go to negative infinity, and as I approach c from the right, I also go to negative infinity. Either way, this is still saying it does not exist. So what I want to do is take a look here. Now I want to find this limit analytically, and then I want to confirm it with the graph. So I want to take a look, first of all, as x goes to 0 from the left of 1 over x. Well, if I approach 0 from the left, then x is negative, right? Because that's 0. If I'm approaching from the left, then all the x values are negative. But the numerator is positive. That means this is going to be negative. Now what's happening as x gets closer and closer to 0, as x gets really close to 0, the denominator is really, really, really small. So 1 divided by something really, really, really small is going to be something really, really, really big. So I know this is getting big, but x is negative, so this is going to be big negative. So it's going to be doing this. Now I'll take a look at this next one. It's the same function, only I'm going to be approaching 0. X will be approaching 0 from the right. Well, if I approach 0 from the right, as x gets really close to 0, x gets really, really small, but stays positive. So I have 1, again, divided by something really, really small, and positive, so that's something huge positive. So that means my graph's going to be doing something like this. Actually, I kind of drew that backwards. I drew it in the direction of approaching, so that would be correct. But typically, when we draw graphs, it's like this. So it's going to come from here. There we go. Now, we can confirm this real quick in Maple. So let's jump into Maple. And I'm going to go ahead and do a plot. The function is 1 divided by x. And x equals, I'm going to say negative 10 to 10, and y equals negative 10 to 10. And let's just take a look at this graph and see what it looks like. And we can see that it's doing exactly what I said it was going to do. Now I'm going to go ahead and make this a little bit bigger so it's easier to see. And actually, I'm going to come back up here and make one quick change. I'm going to add one more command here. Thickness equals, say, 3. That'll make that red line pretty thick. There, now you can really see this guy. So as you can see, as x approaches 0 from the left, it is going down. It's shooting down to negative infinity. And as it approaches from the right, it's shooting up. Now this vertical line here, do you see that's red line here? That's really not there. What's happening is Maple gets down here and it sees the next point is up here, so it connects the dots. This is actually not part of the graph. And I can make an adjustment in Maple so that does not show up. By adding this command right here, discont for discontinuous equals true, you can see now that it does not give me this line in between here that in reality doesn't even exist. Okay, now what about this function? As x approaches 3, I have 1 over x minus 3 squared. Well, as x approaches 3, let's give me a little graph here. 1, 2, 3. As x approaches 3, remember this notation here means both from the left and from the right. So let's approach from the left first. As x approaches 3 from the left, this x is smaller than 3, but it's getting really, really, really close to 3. So as x gets really, really close to 3, this becomes 0, or it goes to 0, but negative. But it's squared, so it becomes positive. So once again, I have a situation where I have a 1, which is positive, divided by something really, really small, but because it's squared, it's even smaller. And once I get less than 1, it's even smaller and positive. So again, this is going to go to positive infinity as x approaches 3 from the left. Now, when I approach from the right, I get the exact same scenario, only in this case, as x approaches 3 from the right, it's always positive, so it's a positive squared, which is obviously still positive, but still it goes to 0. So once again, I have 1 over something approaching 0, so once again, I end up with something that looks like that. And we can verify this quickly in Maple. All I'm going to do is come back up to here, and I'm going to simply change this denominator to x minus 3. And what's going to happen is we're going to see this shift over to where 3 is really what it amounts to. Oh, and it's going to be positive. Oops, I forgot to square it. So let me fix that real quick. I need a paren, and then tell it to square it. Now we're in business. There we go. See, and right here is 1, 2, 3. So this is exactly what we just got done drawing.